All right, for the sake of time, we're not going to do a full lecture on naming. Naming for alkenes is really similar to naming for alkanes. The only difference is you change the suffix from an ane suffix for an alkane to an ene suffix for an alkene. That, and you now want to number it so that your longest chain always contains your double bond. So instead of going through this, what I've done is I've given you guys a YouTube video link. It's like 10 minutes long. The link's on the pod. If you want, you can go through, check that out. Otherwise, you can just pull up these notes or your textbook, and it kind of walks you through how to solve naming for alkenes. Alkenes are really straightforward, and then I even give you a challenge problem at the end to kind of check yourself. All right, so naming of alkenes, kind of boring. I'm not that into nomenclature, but we do want to talk about alkenes in general, right? All right, so first thing I like to start with is alkene stability and assessing what's more stable in terms of an alkene versus another alkene. So we've got one class of alkenes where we have one substituent coming off. These are called monosubstituted. We also have disubstituted alkenes where you can have two substituents coming off. So the top one is that cis or trans? Well, it's cis. The bottom one's got to be trans because those methyl groups are on opposite sides. You can also have disubstituted alkenes where they're coming off the same carbon. And you can have tri-substituted alkenes where you now have three different groups coming off of it. And last but not least, you can have tetra-substituted alkene. All right, now the question is, which of these is more stable? Monosubstituted, disubstituted, tri-substituted, or tetra-substituted? It's a little bit abstract, but I'll give you a hint. It's closely related to the stability of carbocations. What do you guys think? Tetra-substituted, right? So carbocations were more stable when they had more alkyl groups coming off of them. Same thing is true with alkenes, right? So these get more stable the more substituted they are. Does anybody remember why carbocations were more stable with more groups coming off? It wasn't quite resonant, so something similar though. Starts with an H. What was it? Yeah, hyperconjugation. So over here we could say more stable, and this has more hyperconjugation. Hyperconjugation is related to resonance, but it's not true resonance, right? It's just saying you've got weak orbital overlap that allows electrons to be happier. All right, so that's pretty simple and easy. Then we also have to consider some isomerism as well. So let's consider cis versus trans isomers for alkenes. And let's say I've got this alkene versus this alkene. Which one do you think is more stable and why? Check with your neighbor and see if you can convince them. And I'm going to draw in all the hydrogens just for fun. All right, raise your hand if you think the left one is more stable. That's a good sign. Most people have their hands up. Why is the left one more stable? So you said gauche. What is it in a gauche interaction that destabilizes a Newman conformation? Sterics, right? So really the overarching idea here is these methyl groups don't like butting up into one another, right? So this is more stable on the left because it doesn't have that steric clash. So you could say this is less stable due to steric clash. So in general, trans isomers of alkenes are going to be a little bit more stable than cis isomers. Makes intuitive sense though, right? All right, so now what we've got to do is get into the nitty-gritty of how to prepare alkenes. They're a little tricky, but it's related to substitution chemistry, which is why I wanted to master that before we continued on. So let's talk about how to prepare alkenes. There's a couple different methods, so let's stick with method 1 first. So in method 1, you're going to have some sort of leaving group. I'm just going to keep it generic like before. And you've got to have some base. Okay, and this base needs to be a pretty strong base. So let's make a note of that. And during this reaction, what you need to do is find a proton that you can pluck off. And in this case, what you're going to do is look for protons called beta protons. And the beta protons are listed in blue here, and I'll show you how to easily spot them. The alpha position is where your leaving group is attached. So let's write that down. Alpha is the carbon with the leaving group. Beta is one carbon further away. During this reaction, you're always going to go after beta protons, not that alpha proton. That alpha proton is just going to stay put. Okay, so in this step, what we're going to do is grab one of these beta protons. We've got to break a covalent bond, right? So in this next step, what we're going to do is clamp down here and eject off our leaving group. The way I like to think of this is it's a lot like dominoes, right? So they all fall over sequentially and they need to be lined up, and we'll talk about that later. So the product from this reaction will now have a double bond here, and then we'll have our conjugate base, which is HB. Oh, actually no positive charge because it was negative. And do you think this reaction will be first order, second order, third order? What do you guys think? So I'll give you a hint. A first order reaction was like SN1. We said SN1 only relied on one thing doing something, right? SN2, on the other hand, relied on two molecules colliding with one another and reacting. And a third order reaction would rely on three molecules reacting. So would this be second, first, or third? Second order, right? Because there's only two molecules involved in the step. Okay, so let's make a note of that. And all right, during rate determining step, although it's implied. Right, it's implied it's rate determining step because it's the only step. So this must be a second order reaction.
That relies on reaction
between two reagents, yeah. That's just my shorthand. Okay, so what we call this is an elimination reaction, so we abbreviate it as E2, where E stands for elimination, and the 2 stands for the second order process. These reactions are really common in organic chemistry, and they're very easy to spot. They're easy to spot because of two things. If we go back up and we look at it, an E2 reaction must have a strong base. So anytime you see a strong base, you can think of E2. And it's got to have a leaving group on there, and it must have beta protons, right? So anytime you see all of those things lining up, it's a good sign that you've got an E2 reaction taking place. Okay, there's a second method. So let's take a look at that. So method number 2. And in method 2, you still have a leaving group, but in this case, we don't have a strong base. Yep. Okay, so if we don't have a strong base for method 2, what do you think could likely happen? And think back to last chapter. Yeah, a leaving group can pop off by itself. Why can it do that in this case? Yeah, it would give you a tertiary carbocation, right? So the second method is really similar to SN1 chemistry. So let's make a note here. No strong base. That means the leaving group can fall off. This gives you a relatively stable carbocation. And what we're going to do this time is just use a weak base. So I'm just going to call this base with a lone pair. Let's identify this as a weak base. And now what we need to do is, just like before, identify our alpha position and our beta position. In this case, our alpha position is going to be the site of the carbocation. Carbon with a positive. Beta is one further away. Do we have to worry about rearrangements before the elimination? Not in this case, right? Tertiary is already the most stable it can be. So what we want to do is, just like before, identify our beta carbons. And over here we know we've got 3 beta carbons. Does it matter which beta proton we select? No, not in this case. So what we'll do is just grab one of them, and like before we said, it's got to be almost like dominoes, where we clamp these all down. And now we've got a double bond there, plus our conjugate acid. Okay, so this looks a lot like an SN1 reaction, but instead of a nucleophile attacking into your carbocation, a weak base is grabbing a beta proton and clamping down to give you an alkene. So let's make a note. We said before that we must have a good leaving group in order for this to happen. And why must we have a good leaving group? What's the rate limiting step? Yeah, breaking that bond between that carbon and leaving group. So we want to have a good leaving group to favor it falling off and giving you that carbocation. This looks a heck of a lot like an SN1 reaction. So again, this is going to be a first order reaction. Because the rate determining step involves loss of a leaving group. Therefore, what we call this is an E1 reaction. Just like before, the E is for elimination. And the 1 just implies that the reaction is first order. All right, so just like the exam, what would be an easy way to differentiate an E1 versus an E2? What can we do? Yeah, change the concentration of your base, right? We know up here with method 1, our rate is going to be equal to some little k times the concentration of your base, which in this case has a negative charge, times the concentration of our substrate that has our leaving group. And then down here, if we look at the E1 reaction, the rate is going to be equal to K times the concentration of the thing with our leaving group. So no base is involved in the second reaction. That's a really easy way of differentiating between the two. Does that make sense? Okay, so let's take a look at what's going on in lab this week and see if we can determine whether or not it's E1 or an E2 reaction. So in lab, ... We're starting out with cyclohexanol. And what was the acid it said to use? Phosphoric acid. In this case, I'm just going to treat it as generic H+. So generic acid source. What do you think the first step is going to be? Protonating the oxygen. The fastest reaction in chemistry is always going to be proton transfer. Before substitution, before elimination, before any of that, proton transfer will occur. So we'll protonate it. All All right, now we've got OH2. And then we've got our conjugate base of our strong acid floating around as well. The conjugate base of a strong acid, is that going to be a very good nucleophile? No, it's going to be a really crummy nucleophile. Okay, it's also going to be a really crummy base, right? So in this case, do you think E2 is going to be favored? No, we said E2, you have to have a strong base, right? So this is a big hint that it's got to be E1. So if it's E1, what will the next step be? Yeah, the leaving group's going to fall off. All right, so now we've got our leaving group that fell off, which was water. We've got a secondary carbocation, not the best. Is there any way to rearrange this? No, the only thing we could do is go from secondary to secondary to secondary, right? So that's not going to help very much. All right, now what I want to do is identify our alpha position. And we said the alpha position's got to be the carbon with the positive charge, right? So alpha would be right here. We've got beta right here, beta right here. All right, so let's draw in those beta protons. Does it matter which of them we select? No, they're the same, right? Okay, so the next step, we've got to have water act as our base, right? Because it's the only thing around that is even remotely basic. And it's going to grab one of those beta protons. It's going to clamp down. And it's going to give you your cyclohexene plus hydronium, right? So let's think about this. Is the acid catalytic or is it going to be stoichiometric in this reaction? Stoichiometric means do we need to have 1 mole of it for every 1 mole of starting material? What do you guys think? Let's think about it, right? We needed acid up here, but we also kicked acid out at the end. So do you think it's catalytic or stoichiometric? Catalytic, right? Catalytic means you're regenerating it throughout the process of the reaction. So in this case, this E1 reaction is actually an acid-catalyzed E1 reaction. And it throws people because they say, where's the base? And it's like, well, with E1 reactions, you don't need a strong base. In fact, your leaving group can act as its own base to help the elimination proceed. Does that make sense? It's kind of a strange reaction, but I wanted to show you guys it before going into lab this week. The other thing to watch out for is, just like with SN1, watch out for rearrangements if possible. And if there's different types of beta protons, you may want to consider those products as well. And we'll talk about which ones will be major and minor later. Does that make sense? All right. So let's talk about substitution versus elimination, because you can see that they look pretty similar in terms of the two different types. One we said is second order, one's first order, just like SN1 and SN2. So elimination, I'll put up here. And we said E2 relies on the collision between two different molecules. So the example I gave, we had beta protons coming off here. We had some strong base with a negative charge. And we said during this reaction, actually I'm going to grab this one back here. I'm going to clamp down and launch off our leaving group. And then E1, we said involves loss of your leaving group first. So just like SN1, you want to have a good leaving group. And you want to have a relatively stable carbocation. And then just like in the other one, we've got beta protons where we need some sort of weak base. In step 2, to clamp down. And give us HB. And then let's keep track of everything here. We still have our leaving group that got kicked off in each of these, so I'm going to write plus leaving group here. All right. Does that make sense? Pretty simple review. Now let's compare this to SN2 and SN1. And then we'll go back to it. So substitution, we've got SN2. This reminds me a lot of E2, where in E2 we said we need a strong base with a negative charge. SN2 we need a strong nucleophile with a negative charge. So this nucleophile will do the backside attack. And then we launch off our leaving group. And then SN1 we said is very similar to E1, where we have loss of the leaving group as our first step. And then just like before, we only need a weak nucleophile here, meaning it doesn't have to have a negative charge. And we kicked off our leaving group here. And there we go. All right. So now we've got to get into the abstract side of things. If we look at substitution entropically, is this favorable, disfavorable, or about the same in terms of entropy? Yeah, roughly the same, right? So let's make a note of that. So entropically, substitution reactions don't change much. Right, because in this case we go from 2 moles to 2 moles. All right, that makes sense. Now let's go back up and look at elimination reactions. Are these entropically favorable or disfavorable? What do you guys think? Well, let's take a look at the E2 one, right? With E2, we started out with 2 moles, but we're getting 3 moles out. Entropically, is that favorable? Yes. Yeah, we're getting more disordered, right? So let's write that down.
I'm thinking, like, do you want more disordered or not?
Yeah, entropy says the universe should get more disordered, right? So elimination is entropically favorable. Because we're going usually from 2 moles to 3 moles. All right. Now let's go back to the entropy and enthalpy Gibbs free energy equation, right? So who remembers that equation? Everybody's like, yeah, just don't call on me. Delta G equals delta H plus negative T delta S, right? What we just talked about had nothing to do with enthalpy, right? So let's ignore delta H for right now. But let's focus in on this, right? All right, so if we look at this, we know entropy matters for elimination. So would high temperature or low temperature favor elimination reactions? It's a little bit weird to think about. Well, let's go back. Delta S for elimination, should it be positive or negative? Negative, right? We're getting more disordered? Or sorry, positive. Positive for more disorder. Holy cow, I'm like second guessing myself. For elimination. Delta S is positive. We said for substitution it doesn't really matter. It's not really positive or negative. That whole side of the equation doesn't really play a very big role. But we know for elimination it's a positive number. That means that this whole sign here in red should be positive or negative? Negative. So let's write that down. Sorry, my pen's acting up. So if that whole sign is negative, will high temperature or low temperature favor elimination? So let's think about this, right? For a reaction to be favorable, do we want delta G to be negative or positive? Negative. In fact, we want it to have a pretty large delta negative. That way we know it's going to be very spontaneous. So the best way to get it to be as negative as possible is to increase the temperature, right? So in this case, let's write that down as a note. Elimination reactions are favored at high temperature. For substitution reactions, don't change much with the temp change. So this is a really easy way to differentiate between substitution and elimination reactions is look at the reaction conditions. If you've got high temperature, that usually means they're trying to do elimination. If you're applying high temperature for substitution, you're not really doing much besides wasting energy, right? So it's a really simple trick you can use to differentiate between the two. Does that make sense? All right, I think what we might do is just hold there today. But if you guys want to stick around, you're more than welcome to start your pod. In fact, I would encourage you to start looking at it right now with a neighbor and even see if you can do some of the naming on your own. And then when you go home, check that video to see if you named it correctly.